Our next topic is surfaces. And in fact, we've seen some surfaces. I'll mention them in just a couple of seconds. In general, a surface in three-dimensional space is given by some form of equation of the form f of x, y, z equals 0. So if you see something that looks like that, it's probably a surface. So here's an example, the only surfaces we've already seen, which are planes, right? Planes are surfaces. And what did equations of planes look like? They were of the form ax plus by plus cz plus d equals 0. Do you agree that this is some function of x, y, and z equals 0? Do you agree that this is of that form? Okay, so this is an example of a surface in three-dimensional space, and this is, as we already know, this is a plane. Right? So what we want to discuss now is a bit more complicated surfaces. Surfaces in general can be very complicated, and even if they're not that complicated, to draw them is extremely complicated. So we're only going to be able to draw things that are very, very, very user-friendly. Okay. So here's the first example of a non-plane that we're going to attempt to actually draw. So here it is, x squared over a squared plus y squared over b squared minus z equals 0, where a and b are parameters. Okay, you can, if you're finding it difficult to think of a and b in general, put a 2 here and a 3 here. It doesn't matter. Okay. So what we want to do is decipher this. We want to figure out, what does this surface look like? Okay. It's the very first example we have of what's called a quadratic surface, because all the powers are at most 2. Okay. So let's try to figure out what this looks like. The first thing I want to do is rewrite it as z equals x squared over a squared plus y squared over b squared. Okay, and of course a and b are non-zero because I'm dividing by them. Okay, so I'm going to do this very, very slowly because I want to, by this example, exhibit how I tackle such a problem, such a question. And the next examples that we're going to do, I'm going to do a bit more quickly. Okay, so it's hard for me to figure out how do points that satisfy this equation look like in general. So what I do is I try to freeze one of the variables, okay, fix it, and see in the other two what I get. And usually that's more accessible. That's usually something that I can figure out more easily. So for example, if z equals 0, what can x and y be in order for them to satisfy this equation? Suppose z is 0. What can x and y be in order to solve this? Both have to be 0. Do you agree? Okay. So when I plug in z equals 0 here, I discover that the point 0, 0, 0 satisfies this. Does everybody see that? Okay. And that's the only point that satisfies this when z is 0. So if I look at the okay, let's start drawing. If I look at our three-dimensional space, x, y, z, when z equals 0, that's the xy plane down here, the only point that satisfies this equation that sits on that surface is the origin. Do you agree? Let's take a different z. Let's take z to be, for example, 1. What do you get when z equals 1? You get 1 equals x squared over a squared plus y squared over b squared. What is that? What kind of shape is that? Exactly, that's an ellipse. Okay, so when z equals 1, I'm sitting on the plane z equals 1. That's kind of a plane that's parallel to the xy plane. And what I'm supposed to see is an ellipse. X squared over a squared plus y squared over b squared equals 1. All the points that satisfy that are going to look like some ellipse here. Okay, so this is an ellipse sitting on this plane. You're looking at it from the side. Do you agree? Okay. What about when z equals 2? So this was at z equals 1. What about at z equals 2? What shape do you get? It's an ellipse again. Do you agree? Okay, but it's an ellipse with a bigger diameter, right? Because now it equals 2 here. So at at z equals 2, I'm again going to get an ellipse, but this time the ellipse is going to be somewhat bigger. Do you agree? Do you agree that for any z, any positive z that I plug in here, I'm going to get an ellipse? And those ellipses are going to be getting, I need both hands now, those ellipses are going to get bigger and bigger and bigger. Do you see that? Okay, so I'm not going to draw tons of them. How about just one more maybe? Something like this. Do you agree? Okay. What about if I try to plug in a negative z? Let's say z equals -1. What points x and y satisfy this equals -1? Right. It just doesn't happen, right? No combination of x and y would give anything negative here because everything is squared. Do you agree? So whatever this surface is, it does not have a life in the lower half space. Do you agree? It only lives above the xy plane. Okay, so these are called sections. I'm kind of bisecting the surface to try to understand it, to try and decipher it. So that is what I got for trying to plug in various values of z. And I can already get kind of an idea what this looks like, right? I'm starting to picture something that looks like maybe an upside-down kippah, right? Do you agree? Does somebody have a bigger one? Or can I borrow that for a second? Okay, do you agree that what I'm getting is something that looks like this, right? Okay, but let's try to be more precise and understand it better. Let's plug in, for example, x equals 0. What happens when I plug in 0 for x? I get z equals, this is gone because x is 0, I get z equals y squared over b squared. So this is already a shape that lives in the zy plane, right? X is 0. X is 0 means it lives on the actual board, right? And what shape is that? What is z equals y squared, or y squared over b squared? What is that? Right, it's a parabola. Does everybody agree? It's a parabola in z and y. So for x equals 0, I get a parabola, z equals y squared, and if I draw it somewhat convincingly, I'm going to fix these ellipses in a second. What I'm going to get is something like this. Okay, and now I'm just going to fix these a bit, or not a bit. Do you agree? Okay, so this is what I get for x equals 0, and these are what I get for z equals 3, z equals 2, z equals 1. Okay? What do I get, for example, when I plug in y equals 0? If I plug in y equals 0, this is gone. Do you agree? Mm-hmm. And I get again a parabola, but now it lives in the zx plane. Where is the zx plane? It's this. It's coming out at you. Do you see that? Okay, so there's a parabola again that lives, maybe I'll draw it using a different color. It's a parabola that lives, I'm looking at it from the side now. It's a parabola that lives like this. Do you see that? So it kind of comes out at you here. and then goes from behind here. Okay, so this is what I get for y equals 0. Do you agree? Okay. Now, imagining these pictures, even the simplest ones like this, and in fact, it's kind of customary to make all the lines which are behind others, or behind surfaces, to make them dotted. So I'm dotting here the lines that are in the back. It's very easy to do it when you have a board. Maybe it's a bit more difficult in your notebook. But this should kind of exhibit what's in front and what's in the back. Okay? And so this thing has a name. This is called a paraboloid. Paraboloid. And there are various kinds of paraboloids, and this is called an elliptic paraboloid. Because the basic shape is a paraboloid. A paraboloid is the generalization of a parabola in 2 dimensions. A paraboloid, that's the kippah I was holding. And each of the sections is an ellipse. So it's an elliptic paraboloid. If each of the sections were a circle, then it would be a circular paraboloid. Okay? Is it clear what just happened, what I just did? Any questions? Yes? You can plug in values. So when x, for example, is 1, okay, so this becomes some constant, 1 over a squared. It's still a parabola, right? Z equals y squared over b squared plus this constant. So it's still a parabola. It's going to be a parabola not at x equals 0, not at x equals 0, but at x equals 1, there's going to sit here another parabola to the front. Do you see that? These are not easy things to grasp, especially not at the very beginning. Okay, you kind of have, and in fact, it's very different between people. So some people look at this and just see it, and others have to think a lot and get gradually and very slowly used to it, and it poses a challenge for them, and that's okay. Okay, it happens eventually, promise. Okay? So let's do some more of these. Let's take other equations like this, other surfaces, and try to decipher them just like we did here, by plugging in various values and trying to figure out until we feel we understand what the shape is. Okay? So, and these get kind of nice. I like them. So this was the first example. Let's look at, I'm going to write it right away, not as f of x, y, z equals 0, but rather as an equation. Okay? So let's look at z squared equals x squared over a squared plus y squared over b squared. Let's do this one. So it looks the equation looks very, very similar to the previous one, right? The only difference is this square up here. Do you agree? But that is going to make a difference. It's going to be a different surface. So let's see what we get here. So first of all, when we plug in z equals 0, what do we get? For z equals 0, right, again we get just one point, which is x and y equals 0, so again we get just the origin. Does everybody agree? Okay, let me get the blue and the red again. What happens when I try plugging in various values of z, let's say positive, like z equals 1, then I get 1 squared equals this, and again that's an ellipse. Do you see that? So when z equals 1, again I get an ellipse. When z equals 2, I get this thing equals 4. That's still an ellipse. Do you see that? So I get another ellipse at z equals 2. And likewise for z equals 3 and z equals 4. So it starts out very similar to the elliptic paraboloid. Do you agree? And you might be kind of hasty and say, it's again some form of elliptic paraboloid. But it's not. Why? So for example, here I can plug in z to be negative. When z equals negative 1, for example, z squared is 1, and it's again an ellipse. Do you see that? So for negative z's, let's continue the z-axis down here, I again get ellipses, and again they're getting bigger as z gets bigger negative. Do you see that? So I get an ellipse, I again get an ellipse down here at z equals negative 1, and another one which is somewhat wider at z equals negative 2, and so on. Do you agree? Okay, so already it's completely a different thing. So now you might guess, okay, no big deal. Maybe it's just two paraboloids that meet at their at the origin. One sitting up here and the other sitting down here. But that's again not true. And why is that not true? Well, let's look what happens, for example, when we plug in x equals 0. If it were a paraboloid, we would expect to get a parabola, right? What happens when we plug here x equals 0? This is gone. We get z squared equals y squared divided by some constant. What is that? It's a couple of lines, right? It's the line z squared equals y squared. Is points that satisfy that are either points of the form z equals y or points of the form z equals negative y. Do you agree? So I get two lines. I get the line, and when x equals 0, that's when I'm drawing on the board itself, on the plane which is the zy plane, which is precisely the board. I get the line z equals negative y. That's this line. Okay, so this is the line z equals negative, or in fact it's negative y over b, right? And I get the line z equals y over b. That's this line here. These are the lines sitting on the board. So this is z equals y over b. That's what I get when I plug in x equals 0. Do you agree? Good, everybody with me? Say something. Okay. What happens when I plug in y equals 0? I again get two lines, z squared equals x squared, z equals x, or z equals negative x. So I again get two lines, and now these two lines are sitting like this, right? So I can draw them. One is at the front here, and then goes down to the back over there, and the other is at the front here, and then goes behind up here. Okay? So what you should be seeing now, these shapes that you get, the surface that you get, is in fact not a paraboloid at all. It's not of this shape. It's more like a clown's hat, or what's called a cone. Do you agree? In fact, it's, well, in regular language, it's two cones connected at their tip. Okay, but geometrically, this shape is called a cone. So this is called an elliptic cone. Clear? Okay. So this is kind of the process that we go through when we start out from a surface given as an equation and try to decipher what does the surface actually look like. Okay? And this is the ones we can actually do that for, the ones we can actually end up with a drawing that we can really understand or picture, are only the ones that are really the simplest ones, like these quadratic ones. Okay? And whenever whenever we look at things that are more complicated, that have like, I don't know, e to the x or sine x or products of x and y and all kinds of things that are more challenging, you might be able to picture them using a computer graphics, using a program that does that, and there are many of those available online. But drawing them is going to be, on your own, is going to be very difficult. And therefore, picturing them without a computer is going to be very difficult. And even if you let a computer picture it for you, not often will you be able to actually understand what the computer drew. Okay? Our ability to touch these, to actually get a feeling for them, is going to disappear very quickly. Only for the very, very simplest ones. Okay? So I want to draw several more of these, and we'll do that in the next clip.